Hello everyone, and welcome to this video on graphing quadratic functions of the form f of x, or y, equals a times x squared plus b times x plus c, or ax squared plus bx plus c, where a, b, and c are real numbers. And of course a is not 0, because if a were 0, then you wouldn't have a quadratic function. Alright, so in this video, we'll go over a couple examples of functions of this nature and how to graph them using transformations. Right? So we're going to start with the most basic quadratic function, y equals x squared, and then through the use of transformations, which I've gone over in previous videos, so if you could please, if you haven't seen those, check them out. Vertical translations, vertical shifts, horizontal shifts, vertical stretching, compressing, and reflections. We're going to be using these transformations to take the graph of y equals x squared and graph another function that looks like this, say 2x squared plus 3x plus 1 or something. Okay? Alright, so on my first page, I talk a little bit about the graphs of a quadratic function, right? The graphs are these things called parabolas, right? Parabolas. So we have f of x equals ax squared plus bx plus c, again where a is not 0, so it's still quadratic, right? So what we're going to be doing in this video, and what we're going to to make these graphs. Now you could make a table, right? You could do what you do with any function, any equation when you're asked to graph. You could make a table, plug in a bunch of inputs, 7 or 8 points, and find a bunch of outputs, and then plot 7 or 8 or 9 or 10, plot a bunch of ordered pairs on the coordinate plane, and hopefully you've plotted enough to where you can see a pattern forming, and then you draw in the rest of the graph based on that pattern. I mean, you can always do that. Just what I'm doing here is going to be a little, maybe a little quicker, and you'll get an idea for the shape. If you already have an idea for the shape of a parabola, y equals x squared, then you can just simply move that around to get the graph of any quadratic function of any parabola. So what we're going to be doing is taking a function equation looking like this, f of x equals ax squared plus bx plus c, and then through the use of completing the square, and I'll show you this on my examples, we're going to rewrite this in this form. Instead of ax squared plus bx plus c, I'm going to rewrite it as a, right? That's the same a, okay? That a here is the same as this a here. A times, and then the quantity x minus h squared, so this thing's squared, and then afterwards plus some k, right, where h and k are real numbers. So for instance, like 3 times the quantity x minus 1 squared, and then plus 4, right, something like that. This h and k will give me the coordinates of what's called the vertex of a parabola. The vertex is simply the point of the parabola that's either the lowest point if it's opening up, or the highest point if it's opening down, right? It's just that peak point. It's called the vertex of the parabola. Alright, and then you got a couple cases here. If this a, right, if the coefficient on the x squared, or this a here, if it's positive, if it's greater than 0, then your graph is going to be a parabola that opens upward, right, a smiley. So I have a little picture of that here, your vertex with the coordinates, h comma k, and this dotted line going through the vertex straight up and down. This is an imaginary line. It's not actually part of the parabola. It's called the axis of symmetry, and it's a vertical line. It's going to have an equation of x equals some number. In this case, it's x equals h, right, the x coordinate of the vertex. That's the line that if you were to fold the parabola about that line, the two halves would match up. Right, it's symmetrical about that line. And the second case is if this value of a, right, this a, If that's negative, if it's less than 0, then you're going to have a graph of a parabola that's opening downward. Right, again, a little frowny face. Right? Opening down, again, vertex with the coordinates with this h and k that I'm talking about there, and this dotted imaginary line, vertical line called the axis of symmetry, right? The line of symmetry for the parabola goes through the vertex and has equation x equals h. All right, and how we're going to be doing this? How are we going to make these graphs? We're going to graph our equation written in this, it's called vertex form. This f of x or y equals a times x minus h squared plus k. This is called vertex form because you'll be able to easily tell what the coordinates of the vertex of the parabola are. And what we're going to do to graph these is, start with y equals x squared, start with the most basic quadratic function, and then use, one transformation at a time. All right. Like a horizontal shift, and then a vertical shift, and then maybe a vertical stretch or compression or reflection or whatever. Right? We're going to use transformations to go from y equals x squared to this guy, this vertex form. Okay, so I have two examples for you. All right, in the first one, and in each of these examples, I'm asked to do the same thing. I'm asked to graph each quadratic function using transformations, right? So starting with y equals x squared, and then afterwards, based on the graph, determine the domain and the range of each function. Right? So here I have f of x equals negative 3 times x squared minus 12x minus 11. So this is that ax squared plus bx plus c form, where a is negative 3, b is negative 12, and c is negative 11. Alright, so what I'm going to be doing, as I mentioned on the last page, is I'm going to take that equation, that rule, and we're going to rewrite it in that vertex form. Alright, I'll write up the vertex form again here. So where I have f of x or y equals, a, that same a, that's going to be negative 3, times some quantity x minus h to the second power, and then after that plus some number k. Right? And we're just going to have to determine what these a, h, and k are. Right? And I already said a is going to be negative 3, but we're going to do this. We're going to rewrite this in this vertex form through use of completing the square. All right, let me show you that, and hopefully you recall what that is. If you don't, look up another video on that. Just type in, completing the square, and I'm sure plenty will come up. All right, so I'm going to start with, we have f of x equals negative 3 times x squared minus 12x, and then you have your minus 11. Okay. So let's take this away for a second. I'll bring the graph paper back when we actually start making the graphs. Alright, so I remember completing the square. I'll just do a quick refresher off to the side. That was when I had 1x squared, 1, not negative 3. So this is an issue here. We're going to have to take care of that issue in a second. I have a variable squared times 1 plus, and then some number b times the variable to the first power. What completing the square was, it was adding a number to these two terms of variables, adding a constant term to make three terms that were a perfect square trinomial, meaning could be written as the same factor twice, could be factored as a square. How you did that was you took the coefficient of the first powered term, b, cut it in half, so b over 2, b divided by 2, or half b, and then squared it. And then that's the number that would get added. Alright, so you add half of b and then squared. And once you do that, this x squared plus bx plus half of b squared is a perfect square trinomial. Three terms that can be written as a perfect square. And then how can they be written as a perfect square? It would be the variable x plus whatever half of that b was. So b divided by 2, or half b. And if you want to double check, take x plus half of b multiplied by x plus half of b and do all the foiling and combining like terms. You would get x squared plus bx plus half of b squared back. Alright, so this was completing the square. Very, very, very quick refresher. Alright. Now, as I mentioned, in completing the square on the terms with variables here, the lead coefficient was 1, not -3. Right? And again, the only terms I'm focusing on are the terms with variables. Alright, so I'm only going to focus on these two terms right now, the -3x squared and the -12x. Well, the coefficient on the x squared is not 1, it is -3. A very quick fix to that is to factor out that -3, factor out that lead coefficient. Alright, so when I do this, we have f of x equals, and then just from these two terms, I'm going to factor out -3. So -3 comes out, and then in parentheses, right, we're just reversing the distributive property, factoring. Then the first term would be just x squared, and there's your 1x squared that I want, right? And then if I pull out a factor of -3 from -12x, that would be positive 4x that's left over. Right? And you can double check by distributing, right? -3 times x squared would be -3x squared. -3 times positive 4x would be -12x. Alright, so now this x squared plus 4x in the parentheses here, I can complete the square on these. There is 1x, it's in this form, x squared plus bx, right? 1x squared plus a number times x. So because I can complete the square, I'm going to leave a little space in the parentheses there. Alright, so I factored out the -3 from these two terms, giving me this. And then afterwards, I still have the -11. Alright, so sorry, there's not a lot of room over here. There's still the -11 term. I'll write that here. Alright, now comes the completing the square part. We can do that right here. Alright, inside the parentheses. Right, inside this set of parentheses. Now, what do? Alright, you take half. Remember, you take half that b, the coefficient of the first power variable. Half of 4 is 2, and then square that. Well, 2 squared is 4. That gets added. Again, I'm doing this in the parentheses, right? So I'm adding 4, and now this x squared plus 4x plus 4 is what they call a perfect square trinomial. I can rewrite these three terms as a perfect square, like this over here. Alright, now you got to be careful. Alright, you can't just add 4 to an expression and then stop. I have to undo this as well. You know, if you just add 4, look what would happen if I redistributed the -3. I'd have -3x squared, great. I'd have -3 times the 4x would be the -12x, great. You got the -11 at the end, but then distributing that -3 in the parentheses here, you see -3 times positive 4 would give me a -12. There's no -12 up here in the original expression. So we have to counteract this. Right? If I put the -3 back in, right, -3 times 4 would give me -12. So that means that adding 4 in the parentheses really is like adding -12 to the expression that I started with. And to counteract that, you know, if I add -12 or subtract 12, I would then also have to add back positive 12 to, you know, undo it. Right? And I'm going to write that here. This undoes what we added when completing the square. That way, I have an expression that's actually equal to the expression I started with. And you have to be sure to do this. Alright, don't just complete the square in the parentheses here and then add nothing, right? Because that'll totally change the expression and you won't have what you started with. I want to continue to have what I started with. Alright, so finally now we have f of x equals, right, the negative 3 outside times, and then in parentheses here, x squared plus 4x plus 4. Again, the whole reason for completing the square is so I can rewrite it as a perfect square. X squared plus 4x plus 4 is equivalent to the quantity x plus 2 squared. And then after the parentheses we have negative 11, and then the plus 12 we added to counteract the completing the square. Negative 11 plus 12 is plus 1, positive 1. And this expression here, and go ahead and multiply it out. You know, if I were to square the x plus 2, it would give me this, and then multiply by negative 3, it would give me negative 3x squared minus 12x, you know, minus 12, and then I would add 1 to get minus 11. This expression down here is exactly the same as this expression up here. Go ahead and multiply it out. And this is in what they call vertex form. Alright, this is in that vertex form. Alright, so look at this. You know, the value of the a is the negative 3. Right, that's the number in front of the square. Then the x minus h, remember this is x minus h squared. X plus 2 is the same thing as x minus negative 2. So when I have x plus 2 squared, that's really like having x minus negative 2 squared. So the h, the value of h here is negative 2, not positive 2. Right. And then we have plus k afterwards. Well, plus 1, so the value of that k is 1. Right. So a is negative 3, h is negative 2, and k is 1. And the reason, again, this is called vertex form is because now I have this h, and you know, I have it in this particular form, a number times a square plus another number. I have it in this vertex form. I can identify the vertex of the parabola very easily. It is, you know, h comma k, negative 2 for the x coordinate, 1 for the y coordinate. Alright, you'll see this in my graph when I'm totally done graphing. And additionally, because a is a negative number, a is negative 3, the parabola will open down. We're going to see that as well in my graph. Alright, but I'm going to put this thing in the box, this vertex form, back on my graph paper. Okay? Alright, so we're asked to graph f of x equals, you know, negative 3 times x squared minus 12x minus 11. And I just showed you that that's the same as this. F of x equals negative 3 times the quantity x plus 2 squared plus 1. These are exactly the same function. Exactly the same. Right? But I'm asked to do it using, you know, transformations. Okay, I'm asked to do it using transformations. So, bring this new paper up here. What that means is I'm going to start with, the most basic parabola. I'm going to start with y equals x squared. Now I have plotted that many times in previous videos, so I'm going to just plot that in red here real quickly. Now I have my axes drawn, right? My x-axis, my y-axis. So I'm going to have it so that every square represents one unit. So y equals x squared, that has the origin, right? 0 squared is 0. It has 1, 1, right? 1 squared is 1. It has negative 1, 1, right? It's got 2, 4. 2 squared is 4, right? And it's got negative 2, 4, and so on. And you could find all sorts of other points. All right, but I'm going to draw this. It's I'm going to make it a little thin. There's y equals x squared, right? This thin parabola here. I don't want it to take up too much space. All right, there's y equals x squared. Nice parabola opening up, you know, with the vertex. The vertex is at the origin, 0, 0. And then through transformation, I'm going to do one step at a time. I'm going to change this rule, x squared, into this rule, negative 3 times x plus 2 squared plus 1. Alright, again, I went over in my previous videos all these transformations, but I'm going to take it one step at a time. Alright, so the first thing I noticed is that the first thing I'm going to do is I'm going to do my reflection. I noticed that this is, you know, my square. So the square here, x squared, is being multiplied by a negative number. Alright, negative 3. So actually the first thing I'll do is multiply by 3. Alright, so I'm going to take the rule the way it is, and I'm going to multiply the rule by 3. Which is going to cause a vertical stretch by a factor of 3. And all you're really doing is multiplying all the y coordinates by 3. So we're looking at the graph of y equals, you know, again, leave the rule the way it is, and I multiply by 3 and get a new graph where it's vertically stretched by a factor of 3. All the points on the original, I'm just multiplying the y coordinates by 3. So 0, 0 still at 0, 0. 1, 1 is now at 1, 3. Alright, so this point again gets stretched away from the x-axis by a factor of 3. Negative 1, 1 is at negative 1, 3. 2, 4 would be at 2, 12. You know, negative 2, 4 would be at negative 2, 12. So those are pretty high up there. I'm not going to graph those. So here we go. And it's still a parabola shape, still opening up. Right, this little thin guy here. And there's y equals 3x squared. All right. And then after I'm done with all these different graphs, I'm going to put up on another sheet of graph paper the final graph so it looks a lot cleaner. Okay. Alright, so that gives me a 3 in front of the square like this rule has, right? A 3 in front of the square. But it's also negative, right? And when you multiply by negative 1, so I'm going to take this rule now, this 3x squared, multiply by negative 1. And what does that do? Multiply the rule, by negative 1. And that causes a reflection, right? That reflects the graph across the x-axis. So reflects about the x-axis or across the x-axis. Again, all you're doing is if you multiply the rule by negative 1, that means you're just taking the points on the graph of y equals 3x here and multiplying all the y coordinates by negative 1. So we have y equals negative 3x squared. So plotting some of these points, now 0, 0 would still be at 0, 0. 1, 3 would go to 1, negative 3. Negative 1, 3 would go to negative 1, negative 3, right? And, you know, 2, 12 would go to 2, negative 12. And I can put that in here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's negative 12. 2, negative 12. And then negative 2, 12 on the orange graph, the y equals 3x squared, would go to negative 2, negative 12. And you get this parabola here that's opening downward. Right. There's y equals negative 3x squared. Okay, now that takes care of the vertical translation, that takes care of the vertical stretching and the reflection, this number -3 in front of the square. Now I can do the addition parts. Notice that there's a +1 after this first term. So after this first term here, I'm going to throw a +1. So I'm going to leave the rule the way it is and add 1 to the rule. So add 1 to the rule. And again, whenever you do something to the entire rule, that's just what you do to the y coordinates. It'll do a vertical transformation. So I add 1 to this rule, and that's going to cause a vertical shift up 1 unit. All right, so we're looking at the graph of y equals, the previous rule, -3x squared, and then +1. So again, this is going to get pretty cluttered. All right, but again, I'll draw the final result on a separate page. But here's the graph I'm currently at, y equals -3x squared, and then I'm going to be adding 1, meaning moving everything up 1. So 0, 0 was the vertex, now it's at 0, 1. This 1, -3 is now at 1, -2. -1, -3 is now at -1, -2. 2, -12 is now at 2, -11. -2, -12 is now at -2, -11. Every single point on this graph, y equals -3x squared, got bumped up 1 unit. Alright, still a parabola opening down, but there's y equals -3x squared and then +1. Alright, and then finally, lots of stuff going on here. Look at the rule now, -3x squared +1. The only change that needs to be made is, now I'm not doing anything outside, I'm not doing anything to the whole rule anymore. I only need to replace the x, right, inside the square. I need to replace this x with x plus 2. So I'm going to replace x with the quantity x plus 2. Now remember, x plus 2 is x minus -2. The value of that h was -2. And if you replace x with x minus h, and h is a negative number, it moves you left. All right, this will cause a horizontal shift. 2 units left. So then we have our y equals -3 times, and then I'm just the x. I'm replacing just the x with the quantity x plus 2 squared, and then +1. And this is the f of x, right? This is the rule f of x that we were asked to graph. All right. So finally, I'm taking this, y equals -3x squared +1 graph and moving everything left 2. Oops, I drew that wrong. Should be up at 0, 1 here. I apologize. So 0, 1, right? 0, 1 was the vertex of this graph. That gets moved to the left 2 units. Okay, so to -2, 1. There. That's the vertex of this final graph. And then 1, -2 moves left 2 to -1, -2. -1, -2 moves left 2 to -3, -2. And it's again, just this same graph earlier moved left 2 units. Right? So it's this parabola here. And that's the graph of f. Right? F of x equals -3 times x plus 2 squared plus 1. Alright, so I'm going to graph this on a separate piece of graph paper. And then you can always double check your answer. You always check your answers. Alright, so lots of the crazy transformations happening. But then on a separate sheet I'll put up the final results. Right? So we were graphing, remember this was the graph we were trying to make. I changed this to vertex form. In the final graph I ended up with the vertex being -2, 1. Remember, which is what I said it was going to be on that earlier page. Right? Remember this page here where I did the completing the square, changed it to vertex form. We said the vertex would be at -2, 1. And that's where it ended up being after all these transformations. Alright, so negative 2, 1, and I'll label that in a second. Then we had negative 1, negative 2. That location. Negative 3, negative 2. And other points, but it's just this parabola going through these 3 points here, opening down. Right? And I'll label these points. This was negative 2, comma 1, negative 3, comma negative 2, negative 1, comma negative 2. And don't forget to check. Let's just check one of these. Because if these points truly are on the graph of this function, then they should satisfy the equation. The input I have should correspond to the proper output. So let's say this point, negative 3, negative 2 here. If I replace x with negative 3 in the rule, do I get an output of negative 2? Well, let's see. When x is negative 3, negative 3 squared is 9, times negative 3 would be negative 27. So I have negative 27 for the first term. Negative 3 times negative 12 is 36, positive 36. So I have negative 27 plus 36 would be positive 9, and then minus 11 would indeed be negative 2. I do get the output of negative 2 when the input's negative 3. And you can check that for negative 1. When the input's negative 1, is the output negative 2? It should be. When the input's negative 2, is the output 1? It should be, right? All the points that I plotted here should satisfy this equation. Right? Should make that a true statement. Great. So I know that's a lot, right? But and there are you'll see I have a video coming up where we graph parabolas in a little quicker way than this. But this is just to get you used to the transformations again, right? When I do anything to the entire rule that causes some sort of vertical transformation. Vertical shift, vertical stretch, reflecting across the x-axis is an up and down movement, a vertical movement. And remember, when I replace just the x's with something, that causes some sort of horizontal transformation. All right, so really the point of this video is to get you used to the transformations again, and how could I use them to graph a parabola. Alright, so that was my first example. Right, we ended up with this parabola, see, opening down, right? It had a negative lead coefficient, negative value of a. It ended up opening down, and a vertex at that hk, which ended up being negative 2, 1 here. Alright, so I have one more example of this, where again I'm using transformations to graph a parabola, graph a quadratic function, and here it is. F of x equals 2x squared minus 8x plus 5. Now, as I did with the last example, right, we're going to take that 2x squared, and I'll do it on this sheet. I'm going to take that 2x squared minus 8x plus 5, and through use of completing the square on the x terms, the terms of variables, we'll put it in that vertex form, right? And I'll write out the vertex form once again. It's a good thing to do when you have a formula or an equation that you want to memorize. Right? Write it out as often as you can until you get it in your memory. So that was y equals, or f of x equals, a. Well, the a here is 2, positive 2, right? So this is going to be a parabola opening up, times the quantity x minus h squared, and then plus some k, where the h and the k will give me the coordinates of the vertex of this parabola. All right. And this time, because the parabola is opening up, right, the vertex will be at the bottom of the parabola, not like the last example where it was at the top because it was opening down. All right, so get the graph paper. I'll bring the graph paper back later. So from these two terms, I want to complete the square on these x terms. I can't do it yet though. Remember, to complete the square, the coefficient on my x squared term needs to be 1, not 2. needs to be positive 1. So a very simple fix to that is, again, like I did in the last example, just factor this number out of the two variable terms. So I'm going to factor out 2, positive 2 from these two terms with variables. So I do that, pull 2 out, and then in parentheses we'd have x squared as the first term, and then minus 4x. And now in the parentheses I can complete the square. Right? There is a 1x squared in there. So because I'm going to complete the square in a second, I'll leave a little space and then close the parentheses. Right? So we'll add something here. And then afterwards, plus 5. Right, outside the parentheses. Alright, now comes the complete the square part. Remember how to do that. X squared minus 4x. You take half of the negative 4, which is negative 2, and then square it. Well, negative 2 squared is, negative 2 times negative 2, that's positive 4. So again, I'm adding 4 in here. That completes the square on x squared minus 4x. So this x squared minus 4x plus 4 is now a perfect square trinomial. But you got to remember, you can't just add 4 to an expression and think it's going to be the same as the original. It's not. Think about, earlier I factored out 2. What if I were to put that 2 back in? You'd have 2 times x squared is 2x squared. 2 times negative 4x would be the negative 8x from my original. I've got the positive 5 from the original. So what happens here? 2 times this positive 4 would add 8, would have a positive 8. Which would mean that this expression, the way it looks right now, is not the same as the original. So I have to counteract that. This 2 times 4 puts a positive 8 up here. To undo positive 8, I have to throw on a term of negative 8. Again, this undoes what we added when completing the square. Please be sure you're doing this, right? If you don't put on that negative 8, then the expression you have isn't the same that you started with, right? And I want to always keep the same expression, something equivalent to what I started with. Okay, now the whole reason for doing that, right? The whole reason for completing the square. Right, so now I have f of x equals, this 2 pulled out, 2, and then the x squared minus 4x plus 4. Right? The reason I added the 4 in there is so I could write this as a square. This is going to be the quantity x minus 2 squared. And you can double check. Take x minus 2 times x minus 2. That's x squared minus 4x plus 4. And remember, it's just the variable x, and then the other term is just whatever half of that negative 4 was, right? Whatever half of that linear coefficient was, negative 2, x minus 2 squared. And then after that, after the parentheses, you have positive 5 and negative 8. That makes negative 3. Okay. So the a here, this is in that vertex form now. I'll put it in a box. All right, we're done. This is the vertex form is just a number times a square plus another number. Right? I have that here, a number times a square plus another number. So I'm in vertex form. The value of a is this positive 2, right? The same a as earlier. So the parabola is going to be opening up, right? That is a positive number. The parabola is going to open up, right, when I'm done graphing. The h, remember this is the quantity x minus h squared. So x minus, well this is already minus, so x minus 2, the 2 is the h. Alright, and the k, remember the form, it's plus k. Plus k. This is not a plus, but remember, when you subtract 3, that's the same thing as plus negative 3. Right? When I say minus 3, that's the same as plus negative 3. So negative 3 is the value of this k. So I have this h and k. Those are the coordinates of the vertex, right? So the vertex, when I'm done graphing, right, after using all the transformations and whatnot, the vertex will have coordinates, x coordinate 2, y coordinate -3. All right, we're going to see that when we graph in a minute. All right, so I've done all that now. I've used completing the square to change the quadratic into this vertex form. And I'm going to write this again. I'm back on my graph paper. So this f of x equals 2x squared minus 8x plus 5 is equivalent to f of x equals 2 times the quantity x minus 2 squared and then minus 3. All right, these are the exact same expression. They have the same value. They're the same thing. They just look different. All right, we're going to graph this using transformations. All right, so I will write up the transformations on another piece of paper over here, where again we're starting with the most basic quadratic equation, y equals x squared, the most basic parabola. And I'll put that up on the coordinate plane here. So I've got my x-axis horizontal, y-axis vertical. Again, I'm going to have every square represent one unit. So again, you have 0, 0, you have 1, 1. All right, I'll just plot these 3 points and draw the rest in. You have -1, 1. All right, and there's this parabola, right, opening up. Okay, there's the graph of y equals x squared. And the vertex is 0, 0, and so it has 1, 1, -1, 1, opening up 2, 4, -2, 4, and so on. Right, I didn't plot those other points though. All right, now what I'm going to try to do is do one transformation at a time, make one little change at a time, and see how the graph moves to change the rule for x squared into this rule, to calculate outputs 2 times x minus 2 squared minus 3. So like I did with the last one, I like to do the multiplication first. This one has 2 times the square. This is 1 times the square. So I'm going to take this rule and multiply it by 2. All right. So I'll write what I'm doing. I'm going to multiply the rule by 2. So we have y equals 2 times the x squared, right? I left x squared, the rule the way it was, and just multiplying the outside by 2. And that causes a vertical change, a vertical stretch, actually, by a factor of 2. Okay. So that means you're multiplying all the y coordinates of the original graph by 2. Right, all the points will be pushed away from the x-axis, right, stretched away from the x-axis. Now 0, 0 will still be at 0, 0. 1, 1 though will be at 1, 2. Right. See the stretch pushed away from the x-axis. -1, 1 will be at -1, 2. All right, so here's the parabola now. All right. There's y equals 2x squared. Okay, still has a vertex 0, 0. Then, that's before the square multiplied by the square. Then I notice added to the square afterwards is a -3. All right, so I'm going to leave this rule the way it is and just subtract 3 from the rule. All right, so next I'll subtract 3 from the rule. And that'll give me this equation here, y equals 2x squared and then -3. Well, when you do something to the entire rule, it causes a vertical change, and if you're subtracting 3, that will cause a vertical shift, down 3 units. That's an A vertical, right? Vertical shift down 3 units. All right, so I take my other graph, this y equals 2x squared graph, and move all the points down 3. So 0, 0 was the vertex, now it's 0, -3. You have the point 1, 2, move that down 3 units to 1, -1. You had -1, 2, move that down 3 units to -1, -1. And here's the same graph as that y equals 2x squared, right? Just moved down 3 units. There's y equals 2x squared minus 3. All right. And then the last thing I need to do, all right, because I've got the times 2 in front of the square, I've got the -3 after the square, but the thing being squared is not the same, right? This has x squared, this has x minus 2 squared. So I must replace I'll replace the x's. Right? Replace the x with the quantity x minus 2. And when you replace x's in a rule, you're causing a horizontal transformation, not a vertical. And when you replace x with x minus h, and h is a positive, right? H is positive 2 here. That's going to move it to the right that many units. So this is a horizontal shift. Right 2 units. So we have our y equals, 2 times the quantity x. I'm replacing the x in this rule with x minus 2, and then minus 3. And this was the f of x, right? This is the one we want. That's this rule here. So I'd be done now. So I take the graph of y equals 2x squared minus 3 and move all the points to the right 2. So this is 0, negative 3 over to the right to 2, negative 3, which we said was going to be the vertex, right? That's 2, negative 3. Back on the page where I changed it, using completing the square. Vertex 2, negative 3. This 1, negative 1 to the right 2 to 3, negative 1. And then negative 1, negative 1, move right 2. That'll be at 1, negative 1. And it's just, again, this graph moved to the right 2 units. It's the same parabola. And there's the graph of f. Alright, but like I said, this is pretty cluttered. So I'm going to put this on a separate sheet of paper. But just know what happened, know your transformations, right, if you're going to be doing this. Right. So on a separate sheet, I'll graph the final result. Okay, so we had some, we had the vertex at 2, negative 3 was the vertex. I'll label that in a second. We have the point, 3, negative 1. And the point 1, negative 1 on that last graph. And it's a parabola opening up with this vertex. There's a graph of f. Right? And I'll again label some of these points here. So here's the point 3, negative 1, the point 2, negative 3, and the point 1, negative 1. All right, and let's just double check. All right, let's double check. Are these actually points on the graph of this function? So let's see, I'll just take 3, negative 1 here. When the input is 3, when x is 3, would the output truly be negative 1? Would f of 3 be negative 1? So I put 3 in for x. 3 squared is 9. 9 times 2 is 18, so I get 18 for that first term. Negative 8 times 3 is negative 24. 18 plus negative 24. 18 minus 24 is negative 6. And then negative 6 plus 5 is indeed negative 1. So this works. And then try it out for, when x is 1, would the output be negative 1? When x is 2, would the output be negative 3? It should be if this is truly done correctly, and it was. All right, and now that I've got the graphs up, all right, we were asked to find the domain and the range of these functions. All right, so I'm going to go back to that first problem. All right, so here was the final graph from the first one. F of x equals negative 3x squared minus 12x minus 11. Remember, the domain is the set of all the x coordinates that are used. Well, you can plug in anything you want for x, right? There's nothing to make you divide by 0. There's no square roots or even roots in there. You can see on the graph that if you pick an x value, it's going to go to some point on this graph. I mean, this graph is going this way forever, all right? So you pick any x value, and there's a point on the graph with that x value. So the domain is all real numbers, and I'm going to indicate that with interval notation. All right, that's every number from negative infinity to infinity, right? All real numbers with parentheses on those. And if you're unfamiliar with interval notation, please look up a video on it. I've put up one before on interval notation. Okay. Now the range. Range, we're looking at the y-axis, right? We're looking from the bottom up, low to high. What y coordinates are used on points on this graph? Well, can you see that above 1, there's nothing, right? Above y equals 1, there's no points of the graph up here above 1. So we're seeing that the y values that are used are 1, right? 1 is the y coordinate of the vertex, and all the values lower than 1. So from negative infinity, down forever, up until 1. So from negative infinity up until 1, those numbers are used as y-coordinates. Now negative infinity is not a number, so always parentheses on those to indicate that that's not a solution, that's not part of the range. 1 though is part of the range, right? 1 is actually a y-coordinate. It's actually used on the vertex as a y-coordinate. So you put that rectangular bracket, right? You put the rectangular bracket on that to indicate that 1 is part of the range. It is actually a y-coordinate. All right, and then lastly, for this graph here, right, the f of x equals the second example, 2x squared minus 8x plus 5. The domain is again all real numbers, right? So from negative infinity to infinity, right? There's nothing making me divide by 0. Nothing I could plug in that would make me divide by 0 or take even roots of negatives or anything like that. And again, this graph is going that way forever and that way forever. So no matter what x value you pick, there's going to be a point on this graph with that x value. So the domain's all real numbers, but the range is not. Right? The range, and look at the vertex, where the vertex is. See, that is a y-coordinate of negative 3, and then there's nothing below that. Right? There aren't any points of the parabola down here below negative 3. So negative 3 is the lowest value of the range. So I write negative 3, comma, and then there is no highest value, right? Negative 3, and then all the values on the y-axis above negative 3 are going to be the y-coordinates of some points on this graph of the parabola. So from negative 3 up, right, from negative 3 to positive infinity, and again, always parentheses on infinities, they're not numbers. Infinity doesn't actually belong to the range. But negative 3 does, right? Negative 3 is actually a y-coordinate of some point. This point here, the vertex. So I put a rectangular bracket around that to indicate that negative 3 is part of the range. Wonderful. Alright, so I think the thing to take away from this is, one, the graph of a quadratic function is called a parabola. And if your lead coefficient is positive, it'll open up. If your lead coefficient is negative, it'll open down. You can take a quadratic function in this standard form here, right, the ax squared plus bx plus c, and through use of completing the square, you can put it in that vertex form, right, the a times the quantity x minus h squared plus k, where h and k are the coordinates of the vertex. Another thing is that vertex, right, is going to be the highest or lowest point on the parabola. And your transformations, right? If you start with one graph and you do something to the entire rule, you add something to the entire rule or multiply the whole rule by something, that's going to cause a vertical transformation. You're doing stuff to the y-coordinates. But if you take a rule and only replace the x's in that rule with something, you only replace the inputs, that's going to cause a horizontal transformation, which it means you're only changing the x coordinates of the original graph. Great. And then of course domain is a set of all the inputs, x coordinates. Range is a set of all the y coordinates and outputs. Alright. As I like to say at the end of these videos, do the best you can to learn the material on your own before you go looking for help. I've found over the years that people that take the time and the effort to learn something on their own, they tend to remember that material better and for longer, and they're more proud of it. Boost confidence in your own abilities and all that. This is a good thing. So read the material, of course. Read through the author's examples. Perhaps even try to work out the solutions to an author's examples before you look at how the author did them, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously do tons of exercises, practice problems. That's the only way to get better at anything. Practice, right? Practice makes progress. And check for solutions to those if they're made available to you, right? So you can keep track of your progress, see how you're doing. And don't just give up on a problem after one or two attempts. Very often in mathematics there are several approaches that'll work for any particular problem. All right. So if after several approaches though you're still having trouble, I would recommend that you actually read the material again, maybe even a third time, more slowly, more deliberately. Take good notes. Because if you've been working on problems as you should, you probably have a better idea as to what the author wants from you in that section, or you have a better grasp. You'll know more about what the author finds important about that material because they're asking you about it. So when you go back and read again, you'll know better what to look out for, right? You'll know what's considered most important by the author. And you might even catch some things that you didn't catch the first time through, and it'll make working on the problems that much easier. But if after that, if after several read-throughs of the material and several attempts at the problems, you're still having trouble, it is not a sign of weakness whatsoever to go looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online. Videos like this one, or plenty of other ones out there that are better than this one. I assure you they're out there and they're easy to find. Just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is the hardest thing for most people, stay positive. Believe in yourself and your abilities, even through times of struggle and failure and mistakes and frustration. Because it's in those moments of struggle and failure when you have the opportunity to learn the most, and learn the most deeply. Okay, because if you can persevere and persist and make it through and actually learn how to fix your mistakes and push past your frustrations, you'll remember that material far better and far longer than someone who got it right the first time and then breezed through and never gave it a second thought again. Alright, so keep persistent, keep practicing, stay positive, and don't give up. And I'm sure you'll get it. Thank you very much for watching.